So how does all this polymorphism actually work? How does it work behind the scenes? Now, you couldn't go and implement per type exactly all the functions and all kind of pointers and how does it work and what is it doing and all things like that. But it's not the way it actually works. The way it actually works is the following. Behind the scenes, what happens is to every type, not per object, but per type, we go and we create what's called a vTable. We create what's known as a vTable. This is per type. So we have type base, we have this one, and etc. The vTable holds pointers for where the code for that type is actually implemented. So suppose we have 3 functions. So it points to actually where the code is for those functions. Now, when we go and we create a type derived from type base, so we go and we copy the vTable for the base, right? I'm assuming this is base. It's the vTable for derived, which actually inherits from base. So the top half of the table, it doesn't have to be half, but the first part of the table is actually the base table. It's the same table. It's actually copied from the base. And the second part is the part that derived added, all the functionality that derived added. Now, what happened is the following. Since it's actually copying the base vTable, it would point to the same locations. Actually point to the actual same locations. This one will point to there, and this one will point to there, right? And this one will point to there. Actually point to the actual same locations. Unless you overrode it. Meaning, suppose, for example, and these 2 functions point to wherever they point. Suppose that you had a function that was overridden by the derived function. So the pointer here is not going to point to the same location. It would actually point somewhere else, wherever that might be. Now, when you run the actual code, let's see what happens. When we go and we create a data of any type that actually has a virtual function in it. So what we do is we create the object, and the object has what's known on top here. It has a vPtr. That's what it has. And the vPtr points to the table that belongs to that data type. So if this object was actually a D guy, then the vPtr would actually point to this table. If this guy was a B guy, so if this guy was a D guy, if he was a D, right? But if he was a B, let's take a different color. If he was a B, then he would point to over there. Now, when we have a function that's polymorphic in nature, for example, if I go and I write B star vPtr is equal to new D. And then I write vPtr should run some function foo. And let's assume for a second that function foo is this guy. So it's this guy, right? It's the same guy. Function foo is that guy. So what would actually happen is that the compiler will put in code during runtime to go to the vPtr, jump to the table, wherever the table is, and at offset X, in our case at offset 2, right? This is 0, 1, 2, here 2, 0, 1, 2. At offset 2 is the function pointer to the function foo. So the compiler will go and stick your code. It will tell you to dereference the vPtr, and you get to the table, whatever that is, and then you add to that 2, for example, that would be the function pointer to the actual function, and this is the function you want to run, and here are your parameters, right? So this is actually a function pointer. Now, if the object itself is really a D, it would get to the foo down here, and we run this function. If it was really a B, then it would get to the function right here, and we would run this function. So any function that you overloaded or you virtualized in a sense allows us, using another level of indirection, notice we're not accessing the data itself. We are, instead of accessing the data itself, we are using a pointer to get to the table and figure out from there what the real function pointer is. We're using one more level of indirection than standard, more than standard, and then we can go and we can actually run the real correct function. Now, what that actually means is, for example, you have an array, which is a classic example they always give when they deal with polymorphism, and it's composed of three objects: a base, a derived, and a double derived. Now, right now, the derived from the base, and the double derived from the derived. Okay, and we say the following: we call the function. We have a base pointer, right? So we have B star, vPtr, and it's pointing to one of these guys in a loop, even, right? So we use a loop, for example, and we have, for example, I is equal to 0 as long as I is less than 3, and we say plus I, and we say, okay, let the vPtr. We say let's say vPtr equals let's say the array at position I, and then you run inside that. You say, okay, vPtr, run the function foo. Now, how should you know which function should be running? This is the polymorphic step. Right now, here we have a polymorphic step. So how do you know what to run? And the answer is that up here in the actual data, there is a vPtr. This guy is pointing at the B table, at the V table for B. This guy is pointing at the V table for D. And this guy is pointing at the V table for double derived. Now what happens is that the compiler just puts in code here that says, okay, dereference the vPtr, whatever it is, and I know that the function foo is at the same offset in all three tables. Think about it for a second. It has to be the same offset. So it's the same offset in all three tables. That's the offset 2. So I know that this at position 2 is the function pointer to run. This is the function pointer. And therefore, it makes no difference what the real data is. It just functions exactly the same way using one more level of indirection. Now, the only condition for this to work is what we said before, that the table have to be the same of the same. One has to incorporate the next, which is the function foo has to be in the same location in all tables. So what actually happens is that the v table for the derived is the v table for the base plus whatever function the derived added, or this part right here. But it has to be the same for this number to work on all types. Now, which functions actually get to go into the v table? So the answer to that is, well, it depends on how you defined your class. What that means is the following. Suppose we have a class base, and it has, let's say, public, and it has, let's say, virtual void foo that gets an int, and it has an int bar that gets a float. Now, notice that one is actually deemed virtual and one not. So what happens is that the function foo gets put into the v table, while the function bar does not get put into the v table because it wasn't declared virtual. That's how this works. So any function that you declared virtual actually goes into the v table. Any function you did not declare virtual does not go into the v table, and therefore does not allow polymorphism. So the compiler or the linker during compile time will say, oh, if you had again the derived and the base in the same example like we had before, and you called vPtr function bar, right? So there won't be any polymorphism, and it would just use the type of the pointer, which is B star. And then we would call the base function. It won't call anything else. It can't call anything else because it's not the vPtr. But if you call vPtr with foo. So then, since foo was declared virtual, the compiler puts in this entire system in order to figure out how to get to the correct function.